right, so we're looking at the law of sines here. Before we get into what the law of sines is, think back to your geometry days. And one of the things you had to do in geometry was proofs. And we're not going to be doing full-out proofs here. One of the big things you did with your proofs was to prove triangles congruent. And there were 5 ways we could prove one triangle is congruent to another. We had abbreviations for those. I'll tell you one of them was side angle side. We abbreviated it as SAS. So I want you to turn to your friend, and can you come up with the other 4 as best you can? Do you remember what the other ways we could prove triangles congruent to each other were?
Angle, side. Dude, this side is so demotivating. I did so bad at side, angle. Side, angle, side, angle.
Okay.
I really think we should on Friday.
Now, I know this was like 2 years ago, so I don't expect you to have these for sure, but do you recall some of them? Angle, angle, side. Angle, side, angle. Side, side, side. So not on the list is side, side, angle, or it's reverse. If you remember that, like you can't do the ASS. Not a way to prove triangles congruent. Or you'll go to hypotenuse leg. So there's the other one. It doesn't use the letters A and S. It uses H and L. Hypotenuse leg. In a right triangle, if you get the hypotenuse is congruent, the leg's congruent, then you could say the triangles are congruent. HL is kind of the outlier of all those because it has to be a right triangle. It doesn't use the A's and the S's. But these are the 5 ways you could prove triangles congruent. Also not on this list is angle, angle, angle. That would only prove triangles are similar. They have the same shape, but one might be big, the other one might be small. So those are the 5 ways to prove triangles congruent. We are not proving triangles congruent. Rather, we are solving triangles. And we're going to look at these different scenarios. Like if we have this given information, how would we then solve that type of a triangle? Well, one of the skills at our disposal is going to be this law of sines. Notice I have triangle ABC marked out. And across from all the capital letters are lowercase letters. So across from angle A is little a. Across from angle B is little b. Across from angle C is little c. That's the way they're always going to be labeled. The lowercase letters are the sides, and they're across from the capital letter angles. The goal here is to derive the law of sines, derive an equation dealing with the letters A, B, and C that relates some of these sides and angles with each other. Step 1, very lightly, I'm going to draw an altitude from angle C going down. So if you're doing on paper and pencil, do it kind of lightly. The reason why we're going to do this is because all of trig starts with right triangles in SOHCAHTOA. The original triangle wasn't a right triangle, so I'm drawing in this altitude. I'm going to call this length x. It's just like some temporary variable. And the reason why this is helpful is because we don't just have that one triangle anymore. Now we have a couple of right triangles. And let's look at this yellow one first. In that yellow triangle, I want to use SOHCAHTOA. But I've got to make sure I have entire pieces. For example, in the yellow triangle, is this all of the original angle C? So I don't want to use it. Is this length the original length of little c? So I don't want to use it. Is this the original angle A? Good. Is this the original little b? Good. And then there's this x, and it's all of x. So what trig function is going to tie together those 3 pieces of information? Sine, cosine, or tangent? Sine. How about the sine of angle A is opposite over hypotenuse? Good news, we have an equation, but it deals with little x. Eventually, I want to get the x out of there. On the right side, we have this other blue triangle, or this other right triangle in blue now. And And we're going to go through the same kind of thing. In this blue triangle, what entire pieces do you have? Is this the original angle C? So we're not going to use it. But can you write an equation that deals with entire pieces for that blue triangle? Now, this is called the law of sines. Are you using the sine function again? Right? Sine of angle B is equal to opposite over hypotenuse. Two equations. What do those equations have in common? Well, they both have sine. There's an A, there's a B, and the biggest one, x is in both of them. Right? It's the same x. For this equation on the left, we can solve for x. For the equation on the right, we can also solve for x. And then using what we call the transitive property, we could set b times the sine of A equal to A times the sine of B. We are deriving this equation. We don't have to do this but once. And this equation we're deriving deals with comparing the sides and angles with each other. This equation that I have in green is true, but to clean it up a little bit, why don't we get the same letters on the same side? In other words, what if we divide both sides by little a and divide both sides by little b? Which gives us the law of sines, which says that the sine of A over A is equal to the sine of B over B. Not a complex, crazy looking equation, but it's true and it's very useful. Now, with this equation that we derived, we have A and B in there. We don't need this little x anymore. We use the x temporarily to get this equation, so I can go back here and say, forget all of that. Here's what we know. The sine of angle A divided by A is equal to the sine of B divided by little b. Is also equal to, what else do you think? Sine of C over little c. Law of sines. That is the law of sines. One small little thing with this one, then we'll get into some examples. This is true. What else is true is it's reciprocal. You could have said, or we could have done it as A divided by the sine of A is B divided by the sine of B is equal to C divided by the sine of C. This is true. It's 100% equivalent to the original. It doesn't matter which way you do it. Just make sure you're consistent. Either all the angles are on top or all the angles are on bottom, and then the sides would be in the other spot. So law of sines, again, not terribly bad. Calculator necessary. First example looks like this. Organization, I think, is really important in these. And I think the way that I do these, like the organization makes a lot of sense. So I'd strongly encourage you to organize them in the same way. What we have here is a triangle. It's not drawn yet, but there's a triangle ABC that we're trying to solve. We're trying to find out everything about it. What we do know is that the measure of angle A is 70 degrees. The measure of angle B is 60 degrees. And the length of little a is 7. We have to find the measurement of angle C, the length of side little b, and the length of side little c. Those are the things that we have to find. So the things that we were given, they're just there. I didn't have to underline them. I underlined the answers that we're coming up with, part of the organization. First row, A, second row, B, third row, C. First column are the angles, second column are the sides. Nice and organized. It's going to help you to hopefully go through the problems and recognize what you have, what you need, and then make some checks at the very end of the problem. I mentioned earlier that this section is a lot more concrete than the previous stuff, and here's what I mean. There is a triangle, triangle ABC. We know that the measurement of angle A is 70 degrees. The measurement of angle B is 60 degrees. And the length of little a that's across from this one is 7. The stuff that we're given in black means we have a triangle that looks something kind of like this. If I were to go up to some of my original questions, namely this stuff, what we have here is an angle, angle, side. So if you like to organize things like how do I do this kind of problem? How do I always do this kind of problem? Anytime you have an angle, angle, side given, here's how you solve them. All right, let's get after it then. Yep.
Does it matter when we put ABC around the triangle?
No, it's just a visual. You don't even have to draw the triangle. It's just to give you a visual if that helps you to see what you're doing in the problem. How big is angle C? How much? 50. How many degrees are in a triangle? And we've used up 130, so angle C must be 50. Notice there still is a line underneath it because we had to solve that. It wasn't given to us. We had to solve it. So one of your tools is just to know that all three angles in a triangle are always going to add up to 180. So angle C, 50, great. Now let's go after little b. This is going to be with the law of sines. I would say that the sine of 70 degrees divided by 7, that's the sine of a over a, is equal to the sine of 60 degrees divided by b, right? Sine of a over a equals sine of b over b. That is the trig in this problem. Now for some of the algebra, you have fraction equals fraction. What should you do to get this thing moving? Cross multiply. Cross multiply. B times the sine of 70 is equal to 7 times the sine of 60. One more step to get little b by itself. Then what would you do to both sides? How you can get that little b all by itself? Divided by sine 70. So we have 7 times the sine of 60 divided by the sine of 70. Calculator. I like doing alpha y equals n over d, getting the numerator over denominator. Just so when I put it in there, I'm not worried, like, did I use the right number of parentheses? Is it actually doing what it's supposed to do? And so I'm going to enter in the numerator 7 times the sine of 60. And in the denominator, I'm going to divide it by the sine of 70. And I'm getting 6.3 decimal places. I used to have you just go to 2 places for these, but ever since I started teaching the AP calculus, everything always, regardless of the problem, is always rounded to 3 decimal points. So for those of you eventually maybe moving on to that, or even not, I'm just gonna have you go to 3 decimal places. I think it's nice to always be consistent. So we're gonna say this is 6.451. 6.451. Go for little c. As I look at how I calculated this one, the work was a lot of the same stuff. And when I go back to my calculator, I want 7 sine 50 over sine of 70. The last thing I put in there is almost exactly like that. So to maybe save myself some keystrokes, I'm going to up arrow. The only thing that has to change here is in the numerator. It should be 7 times the sine of 50. Otherwise, it's just like the last one we did. And for this one, I'm getting 5.706. Don't have to do it that way, but it is a bit of a time saver. And then there is the answer. Again, it's not a proof, so I'm not doing statements and reasons, but all of my work is off to the side, and in this box is a nice organized answer. I can see each of the angles. I can see each of the sides. The other thing I said is, like, it's nice to be able to check with this. What should always happen here is that the largest angle is across from the largest side. Biggest angle, biggest side. Additionally, the smallest angle should be across from the smallest side. It doesn't take long to check that, but it's a good and useful check because you know if that's not true, you definitely did something wrong. In this case, I feel pretty confident about my answer. Now the triangle solved. Angle, angle, side. Next example. Again, not required to draw this. If you want to draw it, you can. It's up to you. We're looking to solve this, so we need to figure out angle C, little b, little a. Subtract your angles from 180. Angle C is 30 degrees. And then like the previous ones, you're going to use law of sines. The C values are the ones you're going to keep using because you know both of those exact. And once you start doing more of these, you probably can get away with showing less work because you know what you need to multiply and divide by. So again, cross multiply, divide to isolate your variable. Go to your calculator. You can reuse a lot of your work again. Now, something doesn't seem right here. And I like it when like there's a mistake made and we can analyze it. So if I circle this, I make my last check. Is the biggest angle across from the biggest side? Ooh, problem. So I've got to go back, say this can't be true. So maybe that one's going to be off also. When you solve for angle B, or for little b, I'm sorry, 12 times the sine of 130 divided by the sine of 30, what did you get? Does that make more sense now? It's the biggest angle, biggest side. And then for little a, I'm expecting something less than 12. What'd you get? 8.208. Okay. So the quick little check told me I need to look at this again. The biggest angle wasn't across from the biggest side. So now I have it fixed. This one, in case you were wondering, if you drew it out, we knew angle A. We knew angle B. We also knew little c, which would have been over here. That makes this not an angle, angle, side, but an angle, side, angle case. And this ASA is very similar to angle, angle, side. The way we did it was almost exactly the same. Subtract from 180 to get that third angle, and then some law of sine.
Do we have to put that on, like, say we're like doing like a test, do we have to put like angle, side, and angle?
No. No, you don't have to label. This is just for those of you who like to study, like, okay, what am I doing in this situation or that situation? This is telling you, like, in this kind of scenario, this is what you do. But you don't have to identify that if you don't want to. All right, let me give you one more of the same type. Can you solve this triangle? All right, so step one, subtract from 180 to get angle A at 45 degrees. Then you can use law of sines to find the other sides. A is our winner because we know capital and lowercase a, so sine of 45 over 10 equals sine of 60 over B. Cross multiply, solve for little b. Good news is my B is bigger than A, just like angle B is bigger than angle A, so I'm feeling pretty good about that so far. One more time, sine of 45 over 10 is equal to sine of 75 over C. And then when we start solving for C, I'm thinking 13.660. And my quick check, biggest angle, biggest side. Smallest angle, smallest side. So if those are consistent and I went through the entire process, I'm feeling pretty good about my answer. This is another angle side angle case for those of you that were wondering. But that's the idea. Now, a little bit of preview for tomorrow. Earlier, I said you can't use side-side angle to prove triangles congruent. However, we're going to attempt to solve side-side angle triangles. Sometimes we're going to have a problem that doesn't have any solutions. Sometimes we'll get exactly one solution. Sometimes we'll get two solutions. The side-side angle is called the ambiguous case because when you get the problem, you don't know what type of answers you're going to get. So this is going to be the harder of those solutions. For those of you who want to get a head start and start working, 6.1 homework is in OneNote, and you can start working on that. It's going to be due on Friday, so nothing due for tomorrow, but know your time, know how to plan it out. You probably can do some of the first ones especially, and it's all going to be due then on Friday.